Okay, so, hey everybody, welcome back. We're still talking about chapter 27 in physics 46. We're still on chapter 27, which has to do with magnetism. It's our sort of introductory chapter to magnetism. And to wrap up this lecture, let's get into a new topic, and this is magnetic torque. So before we get into magnetic torque, let's actually just do a quick review of what torque is and how we calculate it. So if you've taken physics 45, you know that torque is like our rotational version of force, in the sense that when I apply a force to something, I can cause it to accelerate. I can get its motion to speed up or slow down in some way, and that's really what force does. When I apply torque to something, I can also get it to accelerate and get it to speed up or slow down, but in terms of its rotation. Okay, so if I want to get a rotating object to start moving, then torque is the way to do it. So it's given by this equation here. It's a cross product, so once again, we're using cross products. Tau, which is what we use for torque, is equal to R cross F. So let's get a handle on what this is saying by looking at this diagram here. So this is just an example of a rotating object. It's a baseball bat, and let's imagine that we attach the baseball bat to some kind of pivot, and maybe we can drill a hole right here in the baseball bat, attach it to some kind of pivot so that it gets to rotate around that pivot point. So what's shown here in red is the axis of rotation. That's the point the bat rotates around. Over here, this green point that I'm showing you, that's the point where we apply a force. So imagine I can tie some kind of string to the bat right here and then pull on it this way. That's a force I can apply. Okay, so the R vector is just pointing straight from the axis of rotation to this point where the force is applied. So it's really just going from this point to this point, from the axis of rotation to where the force is applied. And then F is, of course, the force. So R cross F gives you the torque. Now, like any other cross product, we can think of this in terms of a magnitude and a direction. So let's start with the direction. The direction is given by the right-hand rule, and we've done this a million times in this lecture, but let's do it again. When I have the cross product of two vectors, and I want to know what the direction of that is, I use the right-hand rule to give me the answer. So the way it works is, I take the fingers of my right hand, I point them in the direction of the first vector, which is R, and then I curl them in the direction of my second vector, which is F. So you see that? It's R cross F. Now which way is my thumb pointing? It's pointing into the page. So in this case, we'd say the torque is into the page. What does that really mean, though? Well, you can think of it like this. If your thumb is pointing into the page, your fingers are curling in the direction of the rotation that's going to be induced. So in other words, you can think of this like a clockwise torque. If I apply this force, then I'm going to get a clockwise torque out of it. Okay, if I got the other direction, if I, let's say, got a torque going out of the page, that would be like a counterclockwise torque. It's inducing this sort of rotation. That's the idea behind the direction. As far as the magnitude, well, the magnitude of any cross product is the magnitude of the first vector, which is R, the magnitude of the second vector, which is F, times sine of the angle between them. But let's think about that for a second. The magnitude of R is just the distance from these 2 points, from the axis of rotation to the point where the force is applied. Okay, the angle theta is the angle shown here between those two vectors, between R and F. So RF sine theta, that's how you calculate a torque. And of course, if you want the maximum possible torque, then we want a 90-degree angle between R and F. Okay, that's how you get the biggest amount of torque. There's another way to think about the magnitude, which is shown right here, R perpendicular times F. So if we take this R vector and we break it into two components, okay, one of them right here is called R parallel. So it's the one that's parallel to the force. It's the component of my R vector that's going parallel to the force, same direction as the force. R perpendicular is going, well, perpendicular to the force. So if you do a little bit of trigonometry, you can see that R perpendicular right here is just this length times sine of that angle, So I can also write this as, instead of RF sine theta, R perpendicular times F. So it's just sort of two different ways of thinking about torque. They really say the same thing. Now, we all know Newton's second law. The net force on an object is equal to its mass times its acceleration. There's a rotational version of this, okay, for rotating objects. And it says that the net torque acting on an object is equal to its moment of inertia, which is I, times its angular acceleration, which is alpha. So again, it's just like F equals ma, except with torque and rotation. Okay? So that's just a really quick review of torque. I know I glossed over some of the details. So just so we get a little bit more practice doing this, we have to know how to calculate a torque. Let's think about this situation here, where we have a bat connected to a pivot point right here, and then we apply a force to the bat right here at a distance of 32 centimeters from the pivot point at an angle of 35 degrees. The force is going to be 25 newtons. Okay? So find the magnitude and the direction of the torque acting on the bat. Just pause the video, try to work it out, and then we'll come right back to it. Okay, so let's work it out. Okay, so over here, we'll work out the solution. The torque is equal to R cross F. And, okay, the direction, well, that's going to be given by the right-hand rule. Okay, so we'll work out the direction in 1 second. The magnitude, we can think about this as being R times F times sine of the angle theta. Okay, so this is basically a plug and chug to get the magnitude. The distance between the axis of rotation and where the force was applied, well, that was 32 centimeters, or 0.32 meters. The amount of force we applied was 25 newtons, and the angle was 35 degrees. Okay, so if you crunch these numbers, you get 4.588, and the units are Newton meters. So that's the standard unit of torque. It's called a Newton meter, and if we round this off, it's 4.59 Newton meters to 3 sig figs. Okay, so I'm actually going to go back to the diagram to try to figure out what the direction of the torque is. So the R vector goes from the pivot point to this point where the force is applied. The F vector is the force just going straight to the right. So again, we can do the right-hand rule to figure out what the direction of the torque is. So what is it? Well, R goes this way, so point your fingers in the direction of R, curl them in the direction of the force, and then your thumb is pointing into the page. So typically, when we show our coordinates on the plane of a page like this, we're going to have X and Y in the standard way, so X going to the right, Y going up, and then the Z direction is coming out of the page. So if we have something going into the page, that's a negative torque. Okay, so the torque is in the negative Z direction. That's how this works. So the answer that we'd write down for this is, as a vector, since we found the torque is into the page, as a vector we could write this as minus 4.59 Newton meters K hat, just indicating the negative Z direction. All right, so that's how you calculate a torque. That's just a little bit of review as to how that works. Okay, so the next thing is, what does this have to do with magnetism and magnetic fields? So what we're going to show, and this is going to take a little bit of time to build up to, is that if I have a loop of current, okay, it doesn't really matter what the shape is. Here we're going to imagine something rectangular, but I really just mean any kind of closed loop like this, where there's current running through it, and that loop is inside of a magnetic field, you're going to have a torque. Okay? So in other words, there is a torque on a current loop in a magnetic field. Let's figure out how that works. Okay, so this is going to be like our test case. We're going to consider this rectangular loop of wire where there's a height, which we'll just call h. That's h right there. And then there's a width, which we'll call w right there. And it's carrying a current, which is going, in this case, clockwise. The current is I. All right. Now, the loop, this rectangular loop that you're seeing, it lies in the plane of the page. Okay? And at the same time, there's a magnetic field, there's a B field going which way? Well, to the right. Also in the plane of the page, so it's going in the positive x direction. Okay? So there it is. Current loop in the xy plane, uniform magnetic field going in the positive x direction. So we're trying to figure out, is there some kind of torque involved in this? And the way we're going to get at what the torque is to first think about force. So each one of these segments of wire, 1, 2, 3, and 4, they each could have an amount of force acting on them, and that's what we learned about in the previous lecture. So let's start by figuring out the force on each one of these numbered segments of wire. Okay, so remember how this works. The force on one of these segments of wire, F, is equal to IL cross B. And of course, the way we can think about this is in terms of magnitude, where the magnitude of the force would be ILB sine theta, and the direction would be given by the right-hand rule. Okay, so I just copied down the picture. Again, we have a rectangular loop, height h, width w. It's all in a magnetic field going to the right, and we've numbered the segments 1, 2, 3, and 4. So let's start with segment number 1. What kind of force is going to be acting on that segment? Well, it's IL cross B, but that means the angle between L and B comes into play. That theta comes into play. Well, my L vector just goes in the direction of the current, and that's just going straight to the right. My B field is also going straight to the right. So there's actually 0 degrees between them, and that means there's no force. Remember that if you have a wire that's carrying a current in the exact same direction as the B field, there's not going to be a force on that wire. So we're going to get 0 force for segment number 1. Okay, for segment number 2, let's start with the angle. So it looks like my current is going down, but my B field is still going to the right. So there's a 90-degree angle there. We don't want to say the force is 0. What's the direction of the force? Well, we can use the right-hand rule. So remember, it's IL cross B, which means I have to take my right hand and take my fingers and point them in the direction of the current to start off. And then if I curl them in the direction of the B field, then that leaves my thumb pointing up out of the page. So if our torque is going out of the page, that's the same as the plus z direction. So how much torque do we have? Or sorry, force. How much force do we have? It's given by ILB sine theta, except we're taking sine of 90, so that's going to give us 1. So it's just I times the length times B. Okay, so everything is symbolic here. So the current, that's I. Here, actually, let's do something. So the current, that's I. The length of the wire here, that's what we're calling H. And then the strength of the B field, we're just calling that B. And it's in the positive Z direction, so I can write this as positive IHB k hat as a vector. That's the force acting on wire number 2. Okay, wire number 3, this one down here, the current is running to the left, the B field is going to the right, so the angle between them is 180, they exactly oppose each other. And again, that's another case where you're going to have zero force, just like if the angle was 0. Because sine of 180 gives you 0. Okay, the last one is here. So for segment number 4, once again we have a 90-degree angle between the current and the B field. So the force is definitely not going to be 0. Okay, let's do the right-hand rule to figure out what direction this force is going to be in. So we take our fingers on our right hand, put them in the direction of the current, and then curl them in the direction of the B field. The only way for this to work is if your thumb is now facing down into the page. Okay, and into the page is what we call the negative z direction, given the way we set our axes up. Now, the magnitude of this force is going to be ILB sine theta, but once again, we're doing sine of 90, which gives us 1. So if I want to write this as a vector, F4, well, it's in the negative z direction, so I'll have a negative sign right there. The current is I. Now the length here is, once again, h, right? That's the height of the rectangular loop. And then b, k hat. Okay, so what did we just do? We just came up with expressions for the force on each one of the segments of wire in this loop. Okay? So let's summarize all that on the slide. So there's no force on segment number 1. The force on segment number 2 is out of the page, so we can write it as plus h times I times b k hat. So k hat is just telling us we're in the z direction. And F3 is 0, like we said. F4 is going to be minus HIB k hat. So let's think about it. No force here. No force down here either. A force on this one coming out of the page like this. A force on this one going into the page like this. What do you think that's going to cause the loop to do? It's going to cause it to rotate. It's going to cause some kind of torque, which would induce rotation. Okay, so the next thing is to figure out what does that torque look like. Okay, so here's what we have. Again, no force at the top and bottom at 1 and 3. To show that force 2 is coming out of the page, again, the way we show a vector coming out of the page is with this symbol. It's a little dot with a circle around it. And again, that brings to mind an arrow flying out at you. To show that this one is going into the page, we have an arrow, we have an X with a circle around it, which brings to mind an arrow going away from you. Okay? So F2, F4, like this. So each one of those, actually, is going to contribute to the torque. So for that, we'll work it out down here. So again, I've just copied down everything we have, where we've got this rectangular loop, and there's an axis of rotation like this. I showed it with the dashed line. We know there's no force acting on the top or on the bottom, so that's 1 and 3. F is 0. If we talk about number 2 and number 4, those forces are going out of the page for force number 2 and into the page for force number 4. Okay, so we're going to make a calculation for each one of these of torque based on the fact that torque is equal to R cross F. So we can find the magnitude of a torque given RF sine of theta. We can find the direction. You can probably guess what I'm going to write. It's the right-hand rule. Okay, so let's do this for each one of the numbered segments. Now number 1 is really easy because if F is equal to 0, guess what? Torque is also equal to 0. So that particular segment is not experiencing any torque. If I look at segment number 2, that's this one, well, let's think about the angle at first, actually. What is the angle between my r vector and my f vector? Well, my r vector always points from the axis of rotation to the point where the force is applied. So this would be r2. What's the angle between r2 and f? Well, f is coming out of the page, r2 is in the plane of the page, so they actually make a 90-degree angle. They're at a right angle with respect to each other. And, okay, so if I want to get the magnitude of this torque, the magnitude is going to be the magnitude of r, which would be the straight line distance from the axis of rotation to where this force is being applied. That's exactly half of w. It's half the width of the loop. Now the force, the magnitude of the force is I times h times b. That's what we found earlier. Then we take sine of 90 degrees to finish that off. So sine of 90 degrees is just 1. So we have a half w times h, I times b. That's the magnitude of the torque. But if we want to get the direction right, again, we're using the right hand rule. So fingers of my right hand in the direction of r, curl them out of the page in the direction of f, and your thumb is now pointing down in the negative y direction. So as a vector, you could write torque 2 as minus 1/2 WHIB j hat. That just indicates, again, the negative y direction. Torque number 3, that's easy. Once again, if you have no force, you have no torque. And then finally, what's the torque on the fourth segment of wire? Well, here, let's once again draw the r vector, which goes from the axis of rotation to the point where the force is applied. So right there, that would be r4. And so the angle between the r vector, which is going to the left, and the f vector, which is going into the page, is still 90 degrees. They're at a right angle. Okay, so the magnitude of torque number 4 is going to be the magnitude of this r vector. So it's just, again, a straight line distance from the center of the loop, where we have the axis of rotation, to the edge of the loop, where that force is being applied. That's half of w. That's half the width of the loop. Then we have I times h times b. That's the magnitude of that force, as we found earlier. And then we take sine of 90 degrees. Okay, so it's actually the same amount of torque as we have on segment number 2. It's 1/2, what is it, WHIB. Now for direction, well, let's do the right hand rule. Fingers in the direction of r, curl them into the page in the direction of the force. Your thumb is going down. So the negative y direction. So they're in the same direction. The torques are complementing each other rather than opposing each other. And so how do we write torque number 4 as a vector? It's exactly the same as torque number 2. 1/2 WH I times B and then J hat. Okay, so that was just a little bit of a side calculation so we can work out what these torques are. So to summarize, torque number 1 is 0. Torque number 2, minus 1/2 HW times IB in the y direction. Torque number 3, 0. Torque number 4, minus, again, 1/2 HW IB, J hat, meaning the y direction. Okay, so what we really care about is not what these individual torques are. I want to know the total amount of torque acting on the wire, because that will tell me something about how it might rotate. So to take the total, just to add up all of these four vectors, well, these two are 0, so it's just a matter of adding these two, and they're exactly the same amount of torque with this half factor in front. So when you add them together, it just gets rid of the 1/2 factor. So you have minus HWIB J hat. That's what it is. So the next thing to notice here is that we have this H times W thing going on in our equation, and we should recognize what that is. H is the height, W is the width. We're talking about a rectangle, and you take height times width, you're getting the area of that rectangle. So it's actually the area of the loop, interestingly, that's popping up into our equation for the torque. What we have is minus area, I, that's the current, times B, that's the magnetic field, times J hat. And so notice that so far, we've only been considering the case where we have the maximum amount of torque. In other words, my R vector and my F vector were at 90 degrees, which gave us the biggest possible torque. We can also have the loop oriented a different way. It doesn't have to be right in the plane of the page going across the B field lines like this. It can be at any angle you want. So the next thing we have to do is to say that if this is the maximum torque that the loop can have, what's the torque in general if it's oriented at a different angle? That's the next thing. All right, so what we're doing here is we're taking a different perspective now. Before, we were looking at this picture in the XY plane. Now we're looking at it, let's say this is our top-down view. So we're looking from the top down at the loop that we were seeing before. Okay? So what does this look like? Well, this is the X direction, again, going with the B field lines. But now this is the Z direction, okay, going down. And then the plus Y direction is now coming out of the page. So again, we're looking at this same loop of current. Instead of looking at it face on, we're looking at it from the top-down view. And now we're going to allow it to not just be, again, aligned with the B field lines, but at any arbitrary angle. Okay? So now we're going to call that angle theta and say that theta can be anything at all. Okay, cool. So let's take note of a few things. So the first is segment number 4 is over here. And since we're looking kind of down into that segment, you're going to see the current coming up. If we're looking down into that segment, we're going to see the force going this way. Again, that was the negative Z direction on that one. Okay, this is segment number 2. Now we're looking down into that segment. We're going to see the current going into the page over here. And we're going to see the force going this way in the positive Z direction. Okay? And then this is the current running over the top of the loop of wire. So hopefully you guys can kind of see what's going on here. Now, this dashed line is what I'm going to call the normal line of the loop. So it's just a line that points out from that rectangular area, perpendicular to it. Okay? So if I take that normal line, which is, again here, perpendicular to the rectangular area, just going out like this, it makes some angle with respect to my B field lines. So what we've been considering up until this point is that angle being 90 degrees. Okay? And that's when we get the maximum torque. However, that angle, if it's less than 90 degrees, we're going to have a smaller amount of torque. So think about torque this way. Okay? You have a maximum torque times sine of the angle theta. That just gives you whatever torque you happen to have in that situation. Right? So the sine theta factor is always coming into play when it comes to torque. Well, our maximum torque, as we found a second ago, was given by I times A times B. So the current times the area times the B field. If I take that times sine theta, then that's going to give me the torque. Okay, so we're almost there. We're developing this sort of general expression for the torque. There's a few other things we have to take into account here. Okay? So far we've just been thinking this loop of wire has just a single turn of wire. Okay, so just take a single turn of wire and close a loop on it. Well, in reality, what you can do is wrap a wire around the loop several different times. So you could have like 2 turns of wire if you wrap it around twice, or 3 or 4, or any number of turns of wire in the loop. The thing is, each one of those turns of wire is going to have its own torque. So if I wrap the wire around many, many times, I actually get more and more torque. So let's say that the wire is wrapped around the loop n times, and each full turn of wire contributes this much torque. So if we've got n turns of wire, then we're just going to multiply that torque times n. So then we have n times I times a times b times sine of the angle theta. That's going to be our expression for the torque. All right, so we're finally there. What is the general expression for the torque of a current loop in a magnetic field? Well, it's N IA cross B. Probably the most compact way to calculate this is by thinking of it as a cross product. And here's how it works. N, again, that's the number of turns of wire in your loop. I, that's how much current is running in the loop. A is what we call the area vector of the loop. And then B is the magnetic field vector. Okay, so everything else here, except for the area vector, is pretty straightforward. So the area is not something we typically think of as a vector. It's just, width times height, or pi r squared, or whatever the case may be. If it's a vector, it means it has a certain direction to it. And the way we figure out what the direction of the area vector is we use the right-hand rule. Okay? So the right-hand rule for the area vector says we're going to curl our fingers in the direction of the current, and then your thumb is going to be pointing in the direction of the area vector. So here, let's take a look. Let's say I've got current running this way in my loop of wire. So this says I'm going to take my right hand, curl the fingers in the direction of the current. Now my thumb is pointing in the direction of the area vector. Notice if the current were going the other way, like this, I'd curl my fingers in that direction, and now my thumb is pointing the opposite direction. Now that's my area vector. Okay, so that's how you figure out which way the area vector is going. It's either going to be going this way, perpendicular to the area, or going this way, perpendicular to the area. You're going to use the right-hand rule to figure out which one is correct. Okay, so we can actually make this a little bit more compact by defining something called the magnetic dipole moment. The definition of the magnetic dipole moment is it's given by mu is a vector, equal to n times I times a. So basically, it's the same equation as before, but we take this n times I times a thing and just smash it into one term. So, the most concise expression for the torque, and we are going to stop here as far as making this expression more concise, is the torque is equal to mu cross B. And again, these are the same equation. You can just make it more compact by replacing NIA with mu. Okay, so admittedly, I just threw a lot at you. There's a lot to think about. So I want to do a couple conceptual questions so that we really get the idea pretty solid. So I've got a number of different diagrams here, and there are actually 4 different current loops that I'm showing you. Okay? They're all inside of the same exact magnetic field, so the magnetic field is all just pointing to the right. It's perfectly uniform. But I have 4 different current loops in the magnetic field. What I want you to think about is, for each one of these, try to figure out if the torque is equal to 0. Okay? If it's not 0, then try to figure out which direction the torque is in, and pause the video, try to work it out, and then we'll talk about it together. Okay, so here we go. Let's go through the solution. Now, I've actually copied down the picture. So what do we have? We have these 4 different current loops in the B field, which is pointing to the right. And what we have to do is determine what kind of torque is going to be experienced by each one of these. So actually, before we go into this, let me go back to this picture real quick. All right. So it's it's going to be a circular loop of current for each one of these. Now it's pretty clear what's going on here, right? We're looking at the loop face on, and the current is running like this, clockwise. And then in this case over here, we're looking at the loop face on, and the current is running counterclockwise. But in this case, we're looking at the current edge on. So I want to make sure you understand what this diagram is showing. So it looks like the current is going up. What does that mean? Well, it means the side that's closest to you, that would be this side, the current is going up. So you want to think about the current as moving in a circle like this. So on the side facing you, the current is going up. On the side facing away from you, the current is going down. Okay? So it's like we're looking at it on its edge with the current going this way. Now, there's another case of looking at the loop on its edge, and this one is showing the current going to the left. So the way you understand this is the side closest to you, the current is going to the left, meaning it's flowing in a circle this way, okay? Like this. Okay, so hopefully you can see what I'm talking about here. It gets a little bit tricky to visualize some of this stuff. But let's start with loop number 1. So for all of these, the basic idea is the torque is mu cross B, and the magnitude of the torque is mu B sine theta. So it's just any other cross product, that's how this works. And the direction, that's what we determine using the right-hand rule. Okay. So basically, I know what B looks like. For each one of these loops, I have to get a handle on what mu looks like so I can do this sort of calculation. So for example number 1, remember the right-hand rule for the mu vector. I take the fingers of my right hand and I curl them in the direction that current is flowing like this. And that makes my thumb point into the page. So if I want to show that my mu vector is pointing into the page, again I use this symbol, the X with the circle around it, and that would be my dipole moment for loop number 1. It's going into the page. But I'm not done yet, because I have to take that and cross it with B to figure out what my torque is. So, okay, my mu vector is going into the page. I have to then curl my fingers in the direction of B, and now my thumb is pointing, this is really hard to show you, it's pointing down. Okay? So torque number 1 is down. And here, let's think about what that means. So if I have a torque that's going down, that's showing me that this is inducing a rotation like this. Okay, so if you point your thumb down and you of your right hand and you curl your fingers, you'll see that it's inducing a rotation basically around the y-axis. So that's my rotation induced. Okay, let's do number 2. So again, the first thing is we got to get a handle on the mu vector for loop number 2. And so the way you want to think about this one is, again, we're looking at the current loop edge on. So my mu vector is going to be found by taking my right hand, curling it this way in the direction of the current, and now my thumb is pointing in the direction of my mu vector for loop number 2. But let's take note of something here. My mu vector is going to the left. My magnetic field is going to the right. So the angle between them is 180. If I take the cross product of a vector with another, and there's a 180 degree angle between them, then I have 0 torque. So torque on loop number 2 is 0. And that just means there's no rotation being induced in this loop right here. Okay, let's move on to loop number 3. It's pretty similar to loop number 1, except now the current is going the other way. So if I want to get a handle on the mu vector, what I'm going to do is curl the fingers of my right hand in the direction of the current. My thumb is now going out of the page. So my mu, my magnetic moment for the loop number 3 is going out of the page. So once again, I have to take that crossed with my B field, which is going to the right. Okay, so how does this work? Well, I have to start by pointing the fingers of my right hand out of the page. That's what mu is doing. And then if I curl them like this in the direction of B, then what's my thumb doing? It's pointing up. Which I guess we could also say is the positive y direction, just like for number 1 we had the negative y direction, so let's just take note of that. And what does this mean? Well, if I take my thumb and point it up in the positive y direction, my fingers are curling like this. This is showing you the rotation that's being induced in the coil. So it's going to rotate about this axis in this direction. That's the rotation induced. Okay, now let's do one more. The current loop, which I've labeled number 4, here we said that we're looking at it edge on, and then the current that's closest to us is going this way. So take your right hand, curl your fingers in the direction of that current like this, and now your thumb is pointing down. So your magnetic moment is going down like this. And just in all of these examples, just to reiterate, the magnetic moment vector mu is always perpendicular to the area of the loop. So we know it's pointing the right way because it's perpendicular to the actual area of the loop. Okay, now if I take a vector pointing down and I cross it with this B field vector, you got to figure out what that looks like. Sorry, I'm going to have to rotate this a little bit because I just can't move my right hand properly. My mu vector is going down like this. My B vector is going this way. So again, I take mu cross B, and now my thumb is coming out of the page. So that's the idea. This is the torque out of the page, which is the same as the positive z direction. Okay? Now again, what does this mean? If I have a torque, if I put my thumb out of the page, like this, now the fingers of my right hand are curling, well, they're curling counterclockwise. So this one is going to have a rotation induced that's counterclockwise. It's going to start spinning counterclockwise like this. Okay. Now this is all admittedly pretty tricky because we have so many different cross products to keep track of, but you do have to figure out how this works, okay? Okay, so those were the results. And let's do another example. This one, rather than just doing it conceptually and then figuring out what the directions of the torques are going to be, let's do one where we actually make a calculation. So we have a circular loop with a radius of 12.5 centimeters, and it has 10 turns of wire wrapped around it. So again, take a circular loop, wrap a wire 10 times around it, and let's say the current that's being carried in that loop is 1.65 amps. The loop itself is in a uniform magnetic field, which is equal to, in magnitude, to 0.175 Tesla. And the plane of the loop is going to make an angle of 35.5 degrees with the B field line. So if this is my circular loop, you're seeing it edge on like this, and the plane of the loop is making a 35.5 degree angle with the B field lines. So the question is, what is the magnitude and direction of the torque acting on it? Okay, so here is the idea. First, I need to get a handle on the direction. Okay? So my mu vector, it depends on which way the current is going in the loop. So we're seeing the loop edge on, and this is showing you that the side facing you is carrying a current going down and to the left like this. Okay? So my current is going down and to the left like this on the side that's facing you. So if I do the right-hand rule, basically I'm going to curl my fingers in the direction the current is going in, and it looks like my magnetic moment is going like this. So kind of down and to the right is the magnetic moment. That's one thing just to see immediately. But let's work it out. So what we have is, again, I'll just draw one of the B field lines like this. It's going straight to the right. The current is going like this when we see it edge on. Now we were told that this angle here is 35.5 degrees, so let's just mark that down. But we also said that the magnetic moment vector is pointing down and to the right like this, so that's mu. Okay, so one thing we should notice about the mu vector is, again, it's always perpendicular to the plane of the loop, so that's a right angle right there. And that means this angle is just, well, 90 minus 35.5 degrees, or 54.5 degrees. So this is really important. The angle that we actually care about is 54.5 degrees, because that's the angle between my mu vector and my B vector. That's what's going to be relevant in a second. So let's just mark that down right here. That's theta. Okay, so if I want the torque, what is it equal to? Mu cross B. And if we look at the direction, okay, the direction of the torque, I have to do another cross product. Okay, so you guys ready? The right hand rule says I take the fingers of my right hand in the direction of mu, curl them in the direction of B. Now what's my thumb doing? It's pointing out of the page. So the direction is out of the page. So here, let's actually draw that as a vector. If the torque is coming out of the page like this, that means the rotation that's being induced is, well, point your thumb out of the page. Now your fingers are curling this way. That would be a counterclockwise rotation. Okay, so just imagine the loop rotating this way. Okay, now for the magnitude, well, that's given by, for any cross product, magnitude of the first vector, which is mu, magnitude of the second vector, which is b, times sine of the angle between them. So that's why we said over here, the sine of the angle, or the angle between mu and b is important. Okay, let's also remember that mu is equal to NIA. This is just a shorthand way of saying N times I times A. So let's plug that in right here. NIAB sine theta. Now, the area, again, we're talking about a circular loop, just like this. The area of that circle is pi r squared. Plug that in. So we have N times I, pi r squared times B times sine theta. Okay, now we're finally ready to calculate the torque. So here's what it looks like. We have 10 turns of wire, so N is equal to 10. The current in the loop is 1.65 amps. Pi, the radius is 12.5 centimeters, or 0.125 meters, square it. The B field has a strength of 0.175 Tesla, And then the angle is 54.5 degrees. That's what we have to calculate. We're calculating a torque, by the way, so the units are Newton meters. I don't want to do the unit analysis here. It's just going to come out in Newton meters. And the numerical value of this is 0.115 Newton meters, again, out of the page. That's how it works. Okay? That's how you calculate the torque of a current loop in a magnetic field. Okay? So taking this to another example. Okay, let's do one more. In this example, what we have is a loop with 10 turns of wire, and it's shaped like a square. And the side length of the square is 12.5 centimeters. The loop has a mass of 0.45 kilograms, 0.456 kilograms, and the center of mass is right there in the middle of the loop. Okay? So here's what happens. The loop is suspended from strings so that it hangs vertically. Okay, so you have this, this loop. It's just hanging vertically from these two strings. This is what it looks like when we see it face on. If we're looking at it from the side, this is what it looks like when we see it edge on. Okay, so there's no B field. There's no magnetic field yet. Okay? But what we do is we suddenly turn on a B field that has a magnitude of 1.25 Tesla, and it's going horizontally. So this is the magnetic field that we turn on going horizontally. So if we take this loop, starting just hanging vertically like this, if I just move it up to this horizontal position, okay, it's actually going to stay there. So normally, if I took the loop and it's hanging down like this, and I put it up here, we'd expect that it would just flop right over, right? Well, as it turns out, if it's in the magnetic field and there's a torque, then it can actually be held in place like this. So the idea is there's a torque from gravity which wants to make it flop over this way. Okay? There's also a magnetic torque which goes the other way, and they balance out. So that's why it's actually not flopping over. Okay, so that's the situation. Given all the numbers, the question is, what is the current flowing through the loop? Okay, so let's work this one out. Let's take the side view of this loop. So what we've got is the string hanging down like this, okay, connected to this rectangle or the square loop of wire, and we're seeing it from the side. We're seeing it edge on. So we see a current going like this on the side closest to us. There's also a, so that's I. There's also a B field going this way, a horizontal B field. Okay, so let's start with the magnetic torque. The magnetic torque is given by, I'm going to write this as tau B for magnetic, mu cross B. Okay, now let's think about the direction. So if this is the side of the loop that's facing me, and its current is going to the right, if we curl around to the back of the loop, this is the direction of the current, like this, and my thumb is pointing down. So that's my magnetic moment vector, mu. Okay? Now, if I take mu cross B, and I do the right-hand rule on that, I put the fingers of my right hand in the direction of mu, so they're pointing down. But if I want to curl them in the direction of B, then I have to have my thumb pointing out of the page. So again, mu cross B, my thumb is pointing out of the page. So my magnetic torque is going out of the page. And just to reiterate, the intuition behind this is if I have my thumb going out of the page, my fingers are curling counterclockwise. So this is the kind of rotation induced. So this would tend to cause counterclockwise rotation. Now, the magnitude. The magnitude is equal to magnitude of mu, magnitude of b, sine of the angle between the two vectors. That's just another cross product. That's how cross products work. So, okay, the magnitude of mu, as we said, is n times I times a. Multiply that by the magnitude of b. And again, what we're doing here is using mu is equal to n times I times a. And then we have sine of what angle? Well, my b field is going to the right, my mu vector is going down, so there's a 90-degree angle between them. And of course, when we take sine of 90, we get 1. So what do we have? NIAB. But the next thing we can realize is that this is a square loop, so the area of it is L squared. So we have N times I times L squared times B. That's the magnetic torque. Okay? Now let's do the gravitational torque. Because it's not just the magnetic field that's exerting a torque. There's also gravity exerting a torque. So let's figure out how this works. Just to copy down the basic picture, again, we have a string suspending this current loop, and we're seeing it edge on like this. And the center of mass is right in the middle of the loop, like this. So the reason we care about the center of mass, if you recall, this is where we can treat the force of gravity as acting. So the center of mass effectively is where the force of gravity acts. Now, this would be our axis, okay, that point of attachment. That's where the current loop is going to rotate around. So the r vector is going from that axis of rotation to the center of mass, which is where the force is being applied. So basically, we're not going to use any special equation here. Mu cross B is just a special case of torque when we have a current loop in a magnetic field. But the general expression for torque, and remember we used this to derive this one, is just R cross F. So for the gravitational torque, I'm just going to do the standard R cross F. Okay, so the direction, let's think about that. Well, if I take my fingers in the direction of R, curl them in the direction of F, my thumb is going to be pointing into the page. So this is again where we get this idea that we have two different torques, one going out of the page, one going into the page, but they balance each other out such that there is actually no rotation. You don't have this thing flopping over as you'd expect it to. So this going into the page, the torque going into the page, that induces this sort of clockwise rotation. So if you have a torque going one way, inducing counterclockwise rotation, you have a torque going the other way, inducing clockwise rotation, then they just can cancel each other out. Okay, so the magnitude of the gravitational torque, well, that's going to be equal to RF sine theta. It's just any other cross product. You take the magnitude of the first vector, magnitude of the second vector, times sine of theta. So in this case, well, the magnitude of R is just the distance from the axis to the center of mass. Well, the center of mass is just directly in the middle of the loop. So that's half of the length, L over 2. Now the force is m times g, that's the force of gravity. And then the angle is 90 degrees. Notice how my r and f vectors are perpendicular. They make a 90-degree angle. So this is a half L times mg. Now, here's the next thing we're going to do. If you recall, what we're trying to find is the current. And if we're going to find the current, the next thing we have to do is say that the gravitational torque and the magnetic torque are equal, or they balance out. So, I mean, they go in opposite directions, but the magnitudes are equal. That's what I'm getting at. So, the magnitude of the gravitational torque, 1/2 L times mg, equals the magnitude of this torque from the magnetic field, which is N times L, or I times L squared times B. Okay? And again, what we're doing is solving for I, solving for the current. So, if we divide out N, L squared, and B, what we're going to have is mg on top. Okay, we're going to have a 2 on the bottom from this 1/2. We're going to have an L on the bottom because we have L divided by L squared. And then we're going to have N times B. Okay, so that's what it is when we solve for the current. Okay, so the next thing we do is we take the mass, plug in 0.456 kilograms, take G and plug in 9.8 meters per second squared, and then we divide out 2. We take the length, which is 12.5 centimeters, or 0.125 meters. You have 10 turns of wire, that's N, and the B field has a strength of 1.25 Tesla. Okay, so multiply all of that stuff together, and what you get is the current 1.43 amps. So that's how much current we need for those two torques to balance each other out. Okay. All right. So that was kind of the last few conceptual idea that I needed to get you guys to see. So what we're going to do from here on out in this lecture is talk about some of the technological applications of all of these different ideas we've been developing in chapter 27. So what are the technological applications of magnetism? Let's get into that. So the first one, which we've just been strongly hinting at for this entire time, is an electric motor. And the basic operating principle behind an electric motor is this. We know that if you have a loop carrying some kind of current and it's inside of a magnetic field, it's going to experience a torque, which is going to induce it to rotate. It's going to cause it to rotate. So if we want to make something rotate, this is a good way to do it. Just have a loop of current inside of a magnetic field. So this is a basic schematic of what we call a DC motor. And let me just point out a few different things that are here. So the first is we have the north pole of a magnet and the south pole of the magnet on either side, which means we're going to have a strong magnetic field in the middle going this way from the north pole to the south pole. So there's a strong magnetic field right here. Okay, the next thing is we have this wire which is bent into a loop, and it's connected down here to a battery, so that we need actually a battery to get the current flowing in the wire. All right? So since we have this current flowing in the wire and it's inside of a magnetic field, we're going to get it to have some kind of torque. All right? So there's a problem here though. So if we just have a loop of wire connected to a battery, there's going to be direct current. So the current is just going to be flowing one way, and it's going to stay flowing in that same direction the whole time. That's a problem because if we just have the current flowing in one direction and not changing at all, as soon as this loop passes over the vertical position, the torque is going to change direction. So for instance, if the torque was going this way, as soon as it flips over the vertical direction, now my torque is going to go the other way. So that's not really going to do what a motor is supposed to do. Instead of a constant torque just going in one direction, this is going to cause the loop to flop back and forth, okay? So what we need is the current to change direction every time the loop is in the vertical position like this. Okay? And the way we achieve this is with something called a commutator. So the idea behind the commutator is if this end is connected to the positive terminal of the battery, that causes current to flow one way. As soon as it flips over the top position, now it's going to be connected to the negative terminal of the battery. That's what the commutator does. So now the current is going to flow the other way. That's what we want to happen. Another way we could do this is instead of using a battery, we could use an AC power source where the current goes back and forth, but a commutator also will work. Okay, so let me show you real quick, in case you're a little confused about what I was just saying, why do we need the current to change direction? What's up with that? Okay, so I'm going to sketch out for you guys the south pole of the magnet, the north pole of the magnet, and here, let's just draw the magnetic field going this way, which is to the left, from north to south. And let's say that we have, our loop of wire just about to pass through that vertical position like this. Okay, so if the current is going this way in the loop, okay, so the side of the loop that's closest to you, the current's kind of going down and to the right, we know what our magnetic moment vector looks like because if I curl my fingers in the direction of that current, like this, then my thumb is in the direction of that magnetic moment vector, which again is just going out, perpendicular out of the loop like this. Okay. So the next thing is, let's think about what kind of rotation we're going to get in this situation. Okay? So if I want to know about the torque I'm going to get in this situation, it's going to be mu cross B. So I'm going to have my mu vector crossed with my B field vector, which is going to the left. My thumb is out of the page. Okay, so if my thumb is out of the page, that's my torque. And the kind of rotation that's being induced is like this. It's counterclockwise. Okay. Now again, this will be before let's say this is before we pass the vertical position. Okay? So now after we pass the vertical position, where the loop is just straight up like this, now it's facing this way. Okay? So it's just past the vertical position and now it's facing this way. And let's say the current hasn't changed. It's going in the same direction as before. Okay? So now my mu vector, if we do the right-hand rule, so I curl my fingers in the direction of the current like this. Now my thumb is pointing like this, which in our diagram would be kind of down and to the right. Okay? So there's my mu vector. Again, that's a problem because if we calculate the torque now, it's going to be mu cross B. What direction is my torque in at this point? Well, if I take my fingers on my right hand and I point them in the direction of mu, and then in order to curl them in the direction of B, my thumb is now going to be pointing down into the page. Okay, so it looks like my torque has reversed direction as my current loop has passed over this vertical position. Okay, so again, we do not want this to happen in a motor. We want the torque to just be going in one constant direction to keep the motor spinning in the same direction. We don't want it to go back and forth like this. So the way to avoid the torque from going back and forth like this is to have the current switch direction as soon as the loop passes over that top position. Okay, and that's the whole point behind a commutator. If we want to get that steady rotation, the current actually does have to flip every 1/2 turn. Okay? So let's take a look at an animation of this, because this is definitely a lot to wrap your head around. So again, we have our current loop right here. It's connected to a battery, but we have commutators. So we can switch from connecting to the positive and negative terminals with the commutator, which can flip the direction of the current. And we have the B field going straight to the left like this. Okay? So again, as we pass over that top position, the current flips, allowing us to keep a steady torque that keeps going in the same direction and doesn't change. If you want to look at this animation again, I have a link to it down here on the slide. Okay. The next thing is loudspeakers. And really, this applies to anything from speakers in your car to your home audio system to in-ear headphones, whatever the case may be, any kind of loudspeaker. The principle is basically this. If we have a magnetic field, it will exert a force on a wire that carries a current, right? We saw that way back at the beginning of this lecture. If you put a wire that carries some kind of current through it, if you put it in a magnetic field, it's going to experience some kind of force. Okay? So this is how a loudspeaker is basically set up. We have a coil of wire right here, and it's wrapped around a magnet. So there's going to be a really strong magnetic field right around this coil. Okay? Then what we're going to do with this coil is we're going to run some current through it. But we're not going to run just like direct current, the type you get from a battery. Instead, we're going to run alternating current with some kind of frequency. Okay? So we've got this alternating current going into the coil. Okay? And as soon as I have current running through this coil, because there's a really strong magnetic field next to it, I'm going to have this coil experiencing a force. Now, if the current is going one way, it's going to be pushed out like this. And if the current is going the other way, it's going to be pulled in like this. And since I have alternating current, it's just going to be going back and forth, in and out like this. And whatever frequency I give it for the input source, I'm going to get this cone, this is what we call this piece, the cone, moving back and forth at that same frequency. Okay? So whatever frequency of this current that I put into it, I'm going to get that same frequency of this back and forth motion of the cone. Now, this cone is pushing against air, which is right next to it. And if I have this back and forth motion of the cone pushing against the air, that actually creates a sound wave, which then moves through the air. Now, crucially, that sound wave has the same exact frequency as whatever this current that we put into it. Okay, so here, if we take 60 hertz as the signal that we put into this, that means the current is going back and forth 60 times every second. That also means that this cone is moving back and forth 60 times every second, and that means we're going to get a 60 hertz sound wave coming out. Okay? That's the idea. That's how you produce a sound with a given frequency. And so, it just depends on what kind of signal you put into this as to what kind of sound comes out at the end. That's how a loudspeaker works. So, here's a little bit of an animation. Really simplified. Again, we've got this alternating current going through this coil. That coil is in the presence of a really strong magnetic field. And because of that, it experiences a force which goes up and down, up and down. It moves the cone. That creates a sound wave in the air. And that's really how a loudspeaker works. All right, so that's going to do it for chapter 27. And that's all we're going to say for now about magnetism. There's some practice problems at the end of this lecture. You can check those out. We don't have time to go through them right now, but answers to all these problems are up on campus. All right? So the next time I see you, we're going to start chapter 28, which deals with the actual causes of magnetic fields. And I'll see you next time for that. So be safe, be healthy. I'll see you next time.